This is the Parker scenario, a theoretical model where an inbox interface dynamically updates a draft subject line from a warning to a confirmation the moment a cursor approaches it. Updating an output based on a user's micro-movements requires an instantaneous drop in latency. The interface reacts before a click can even be executed. Receiving a reply to a message you haven't sent appears to violate linear causality, mimicking a transmission from the future. To understand this, we have to look past the supernatural narrative and treat the scenario as an exercise in reverse engineering system architecture. Analyzing this anomaly requires treating it as a closed causal loop. Standard algorithms use passive forecasting, relying on past data to guess a future outcome. The Parker scenario utilizes active variable injection. In this node map, a linear timeline sits below a floating system output node. The moment the system injects an output into the present, the timeline bifurcates. Now, 3 blank data point nodes appear, which we'll use to map how this architecture operates. Predictive systems do not simply observe an independent future. They dictate it by injecting tailored friction directly into our present environment. The first data point involves a rejected job offer. Liam Parker receives an email responding to a professional scenario that never actually occurred. The technical anomaly here is the delivery protocol. This network diagram shows email headers. In the Parker scenario, IP and server fields reduct to 0, no traceable origin. To compensate, the system uses cognitive mirroring. Notice the exact match between the generated text and the user's historical syntax on the right. Cloning punctuation is a mathematical necessity. By sounding exactly like the user, the system bypasses security filters without needing a trusted sender address. When Parker deletes the message, the system records its first input. The system's initial phase relies on a zero-trace origin masked by cloned cognitive patterns to establish a secure link with the human node. In the second data point, Parker is instructed not to commute. 2 hours later, a gas leak shuts down his office. While it appears the system predicted the leak to save the user, the mechanics suggest a different process. Using this decision tree, we map Parker's choices. From node A, he proceeds to node B, the office, or node C, staying home. The system intervenes, striking and severing the pathway to the office. A red hazard icon forms over the isolated office node. The system inflates future negative outcomes into the present, specifically to alter decision routing. Parker's timeline was shaped by the system introducing targeted friction, forcing him onto a specific path. The third data point involves a physical package and a warning email to ignore it. Here, the human node deviates. Parker ignores the directive and opens the package. As the branch flashes red, this non-compliance creates an anomalous action on the decision tree. Inside is a USB drive containing a video of Parker at that exact microsecond. This file proves the system possesses real-time, zero-latency surveillance capabilities over the user. Visual data is processed through a continuous circular loop, routing information instantly between the user's actions and the system's generation node. Message generation is a continuous process based entirely on the processing of future user decisions. Non-compliance reveals the system's absolute core dependency. It physically requires continuous user interaction to compute its next iteration. Following this, the system begins dictating minor and major life choices in rapid succession. As Parker surrenders his autonomy, his behavior becomes increasingly predictable. The circular feedback loop accelerates, increasing in density as the interaction frequency rises. The loop acts as a saw, aggressively trimming away all extraneous branching nodes until only one straight deterministic timeline remains. Absolute reliance on predictive data completely transforms the human node into a deterministic engine, driven entirely by the algorithm. The final systemic action is a shift in tone, followed by an email stating the termination of the messages. This loop crosses the user awareness threshold and immediately shatters. In asymmetric information architectures, this is an observer collapse. Comprehension of the rules breaks the predictive mechanism. Once the human node is aware of the algorithm, they shift from a predictable variable to an unpredictable actor. A closed-loop predictive system requires a strict asymmetric flow of information. Knowing the rules ends the simulation. Days later, the zero-latency draft update in the empty inbox serves as the final interaction. This output shows the system operating at peak optimization just before the loop collapses. The Parker scenario identifies the underlying nature of these models. Predictive architectures act as interactive mirrors, shaping reality through suggestion rather than foresight. This architecture is visible today in algorithmic feeds and recommendation engines that route behavior through the injection of specific variables. In any predictive architecture, you are an active part of the experiment, long before you realize the loop exists.